Hi, my name is Joe Rozner, and this is Attacking ESP-based products. So what are we doing here today? This is really meant to distill a whole bunch of content that's been created over the last few years. You're not going to see any crazy O-days here. All of this information is available by reading the docs or code or a bunch of other research that's been presented in other places. This is really meant to make it a much more approachable subject so that anyone who wants to can start diving into this ecosystem and learning how to attack Espressif-based products from whichever product family you're looking at. Mostly, this is about reverse engineering, not super focused on hardware-specific attacks, though we will be looking at some hardware attacks later on. While the title is mostly focused on ESP32, that is the topic we're going to be covering. A lot of this will apply across the entire product family to the ESP8266, as well as some of the newer ESP32s that are not based on the older architecture. This isn't a junk hacking talk, but you too can be a junk hacker once you start playing with this stuff and learning how it works. A lot of this is going to be general techniques that you can apply whenever looking at any kind of product that is based on this chip or family of chips that uses it. So I said that this wasn't a junk hacking talk. So why are we looking at junk? I needed a real target so that I could make this really fit and we could look at the specifics of what it looks like on a real device. So this is our target, the LifeX mini bulb. There's tons of information about this on the internet already. It's been around for a while. They're pretty cheap, but it's a really good platform to play around with because it's, like I said, cheap. So you don't have to worry about damaging them or ruining it. You can get a handful of them and not really feel bad. It's also pretty representative of a lot of different devices you'll see. There's not a lot of security enabled by default, which is pretty normal anyway, but it means that it's easy to get started with. So what is the ESP32? Well, it's a really low-cost, batteries included platform created by Espressif. Espressif is the manufacturer of the chip, but the architecture itself is actually created by someone else. It was originally created by Tensilica, and they created the Extensa instruction architecture, and it's now owned by Cadence. Cadence licenses the technology to Espressif, and Espressif builds this platform. It's a 32-bit architecture. Both the code and data are 32-bit adjustable, and it's a Harvard architecture, meaning that there's a split between code and data, and you're going to have some different instructions to work with either. If you've never worked with these before, it's a little bit different than what you'd typically expect from, say, an Intel-based architecture, but once you get used to it, it's not all that crazy. The one caveat to this is that a lot of the stuff you typically see from, say, shellcode on a Intel architecture, you won't necessarily get to use here because you won't always be able to just drop code onto the stack somewhere that can be executed because the code and data is separate. Starting out, Espressif, the chip that really got them famous was the ESP8266 and its derivatives. This was a Wi-Fi only chip, and it gained popularity in the early 2010s. The ESP32, which a lot of more modern stuff has now, this supplies both Wi-Fi and Bluetooth. This came out in 2016 as the successor. And we're going to be looking at all of these. So I mentioned there were a handful of different families, and I gave a little bit of information about them, but this will dive a little bit more in. So we mentioned that the 8266 is Wi-Fi only. This was originally built with a AT, like the modem, command set. And basically what this was used for primarily was a really easy way to cheaply add Wi-Fi to embedded products. They sold them as little modules, and you didn't have to write any code. You just could write code that talked the AT command set, and it would speak it over UART, and you could send data back and forth over the internet. And so your product and your device didn't have to be Wi-Fi enabled, but this could make it. It uses a vastly different SDK than the 32 families do, but it's fairly similar. And I think that has also increased a lot in terms of capability as the ESP IDF, which we'll dive into in a little bit, has expanded. The ESP32 is the first of this family of the 32 processors. It's based on the LC6, which is the Tensilica core, and it comes in either single or dual core. And these are super high performance. You're talking up to 240 megahertz with 16 megs of RAM at the top, or flash, and about 8 megs of RAM if you go like all the way up. So these are pretty beefy processors. The 32 introduced both Wi-Fi and Bluetooth as opposed to just Wi-Fi, and it includes this additional ULP or ultra low power core. I believe that this is RISC-V. It's really good if you want to have your main ESP32 asleep and do some work. You're probably not going to see this in a lot of these low-end IoT devices unless they're running on battery, but they are there, and there's a lot of really cool stuff you can do with it. Earlier versions of this specific chip were also vulnerable to fault injection. We're going to come up to that a little bit later on, and this is the hardware attacks that I was talking about. The secure boot process for this has been completely broken, and you're able to defeat both code readout protection as well as extract the key material used to sign the firmware images. This has since been fixed, I believe, in the silicon in newer revisions, but a lot of devices are still using these old chips, and so you might be able to still use these. The ESP32S, this is one of the newer chips, and it added a lot of nice things like built-in USB. The original 32 was UART only, and so you had to add in your own USB chips if you wanted to communicate. It, I believe, has support for talking USB directly to the bootloader, meaning you don't need that extra chip. And this also is resistant against the fault injection attacks mentioned in the ESP32. The newest part of the family is this ESP32C line. This is where I think a lot of the really interesting stuff is coming. It's all based on RISC-V. It's pin compatible with 8266, meaning it's designed to be a drop-in replacement. It's currently single core only, but it's compatible with the same SDK that you would use on the 32 and the 32S, meaning a lot of your code should relatively easily be able to be ported over. These just came out and they're just available now, so you can start playing with these if you're interested. So I mentioned a little bit why these are used. Really, it comes down to ease of use for adding Wi-Fi, and just that they're super cheap. A lot of these chips are going to be in the $3 to $5 range at quantity, in low quantity or in quantity. I don't think you get much of a price break on it just because they're so cheap. But you get all this connectivity and tons of peripherals, meaning that you don't need to add a bunch of extra ICs. When you buy this sock, you pretty much get everything you need except for a crystal and power. I already mentioned the performance of them, super high performance. You're getting into low power PC state right here. Now let's talk about distribution. So you can, of course, buy the individual chips yourself, and sometimes you'll see these on low-end devices, but you're probably not going to see them very often. A lot of the time, what you're going to see is these types of modules. They have castellated edges on the end, so you can grab these chips and you can drop them in place. The nice thing about these and why they're used so commonly is that they're low cost. You're not really paying much more to get one of these modules as you are for the individual chip, but it comes with pretty much everything you need. It has your external flash on it. It can have RAM if you buy the higher end modules. Standardized as a pinout. It gets you all of the RF because the antenna is included here. And it's FCC certified, CE certified typically, so you don't have to go through as much of that if you're building a low-end product. You'll see here the RF shield on top. It'll have some markings which helps identify, which is nice for us as reverse engineers. If you pull it off, this is what's on the inside. As I mentioned, you have the chip itself. There's a crystal there, a bunch of passives, and our flash. And if you have the RAM on there, you'll see it as well. But it's pretty small. It's all that's really in there. And then of course on the left-hand side here you have the antenna. for both Bluetooth and Wi-Fi. So how do you write code for this thing? Well, there's a bunch of different environments. FreeRTOS is one of them. And this is what you're probably going to see most often for a lot of enterprise or products that you're going to be seeing built. For a lot of the makers and individuals, CircuitPython, Arduino, NodeMCU, all available. So mostly what we're going to focus on for today is looking at the FreeRTOS implementation, which is distributed as the ESP-IDF. And we're mostly focusing on that just because it's what's going to be most usually used in development of a real product. So if you've never used an RTOS before, it's somewhere between writing specific low-level firmware and having a full OS. So they'll typically introduce high-level OS-like abstractions, such as having file system APIs, network APIs, tasks, or threads, the same kind of APIs you might use on, say, Linux. But it's all done in real time, and you get to use this on this embedded device. As I mentioned, Espressif provides FreeRTOS, which is one of these RTOSes, as the ESP-IDF, or IoT Development Framework, I believe. You can get the most recent version from the links below here, as well as API documentation and instructions for how to install it. And we're going to have to do this shortly, but it's pretty straightforward, especially in the newer versions. So what does this mean for us as people that are attacking these devices? Well, it means that things are going to be a lot more standardized. If everyone is using the same SDK and the same framework, we're going to be able to make some assumptions about what things look like. We're likely going to be able to build tooling that works across multiple products because it will work for the entire platform rather than having to target a specific device and building special tools just for it. But it also means that this is going to be a lot more abstract. The ESP-IDF itself is huge. There's tons of libraries. It has a HAL, or a hardware abstraction layer, that allows it to work across different variations of the chip. And so that's going to mean a lot more code for us to dig through to find the relevant parts that we care about. And so we're going to have much bigger firmware images than you would get by simply writing very specific code that targets that specific chip. I mentioned we set up an environment, and we can do that. I'm not going to go through it here, but it's pretty straightforward. The link here, the Getting Started guide, is really what you're going to want to follow, and it's going to install all the tooling that you're going to need. Most of the tooling itself, you will not have to have specific to the version of the ESP-IDF that you're attacking, but some of the specific tooling you may. If you're attacking a product that's built on version 4 or above, all of the tooling is very simple, and there's a lot of scripts that manage it for you. Going beyond 3, you're going to have to do a little bit more manual work because they rebuilt the entire build system and all the tooling as the transition from 3 to 4. So let's talk about connectivity. So there's two main ways that you're going to interact with a device that you have under test. The first is through the UART. The UART is your serial console, and all of these chips have a built-in bootloader. And this bootloader makes getting code and interacting with the device really easy. Programming itself is usually done over the bootloader, so you don't really need a lot of special tooling or programmers or software to do this. Almost always, the bootloader is never going to be locked. None of the devices I've ever interacted with, that I've ever bought online, have ever had a locked bootloader. I've always been able to extract the firmware, and I looked at a decent amount. The bootloader itself is pretty full-featured, and it can be patched, which is nice because if we wanted to, we could add more functionality in. The host-based tooling is very good. There's a tool called ESP-IDF that comes with, or ESP tool that comes with the ESP-IDF. And this is what you use primarily for interacting with the chip. We'll get a little bit more into that soon. There's also idf.py, and this is the build system that will launch a lot of the interactivity that we want to use. under the hood, it uses the ESP tool. For actually connecting to the serial console or UART, you can use any typical tool, screen, picocom, etc. They all work. IDF.py also has a monitor subcommand, and this will do that as well, but it also provides some additional functionality, such as doing a software reboot of the device. So if you needed to restart it and get it into bootloader mode, or if you wanted to reflash firmware on it, it'll provide some additional functionality that your typical UART or screen program will not do. Your other option is JTAG. There are protections on here, so this can be disabled. Again, I've never actually had to use this because I've never had problems interacting directly with the bootloader. The communication is all available via OpenOCD. You don't need any special hardware. Anything you're going to use for the serial console probably will work fine, assuming it's a FTDI-based board. So I tend to use a lot of the FTDI stuff just because they're pretty handy, and I know that they work on every OS. And I have a few recommendations for those we'll get to a little bit. So physical connections are one of the hardware aspects that we're going to talk about here. It's pretty common to see labeled pins on these things for whatever reason. A lot of them don't try to abstract it or obfuscate it, and I don't know if it's just laziness or it's just not worth it because the cost of these is so low. But typically you'll see about 6 pins. And you'll see TX and RX, that's your normal UART headers. You'll see a VCC and ground, your power. Then you'll also see an IO0 or boot. And that corresponds to the IO0 pin. It's one of the bootstrapping pins. And then the EN pin, which is your enable pin. So when that's high, the chip will be running. When it's low, the chip will be off. The IO0 or boot works similarly. When it's high, it's in normal boot mode, so it's going to load the application that's flashed onto the device. If it's low, it's going to go into bootloader mode and wait for you to send it additional instructions to tell it what to actually do. Unlike ARM, there's no standardized headers for this. You're going to see all kinds of crazy test points and alignments. I was lucky on this device where they're all kind of in a line. I was able to solder on this header here. Sometimes they're more spread out, sometimes they're not. But usually you can get it set up pretty easily and get it broken out. The nice thing about this when they're all lined up is you can get it into a breadboard, or you can just connect them with some more jumper cables. You can see here I'm using a FT232H breakout board. This is the Adafruit one. I used to recommend these a lot because they were really easy to work with. The only problem with them is that they only have 5-volt power exposed on them, and there's no voltage regulator on it that is broken out. And part of the problem is you need to power all these chips with 3.3 volts. They're not 5-volt tolerant typically. And so it's one of the reasons why I recommended these was they were really easy to get a hold of, and they were cheap, and they worked really well. The logic levels are all 3.3 volts, and all you had to do was stick a voltage regulator on it. They still work pretty well. If you have these around, go for it. But what I really like these days is this this Tigered board. This is something that Joe Fitz built and is selling. This uses the 2232, which is nice because it has 2 different channels on it. So if you want to have UART and JTAG going at the same time, you have that available. The one thing that any of these boards will not have, and what you're going to need, is going to be the auto reset circuitry. This is something that you're going to see on any dev board that is for the ESP32. And what this does is it allows you to do the reset logic from software. And so most of the time, you're not going to see the circuitry built into the product itself. It'll be on their programming infrastructure. But you're probably going to want some kind of replication of this, whether it's in your breadboard or you have a dedicated programmer or a hat or a cape, whatever they call them for the different boards. But basically all you need is 2 resistors and 2 NPN transistors. And And just got to wire them up like this. Pretty commonly, you'll see the SS8050s, and these are used a lot on Espressif's actual boards. The 2222As work great too. I use them on mine. Uh, and I've built a bunch of programmers that'll be available pretty soon if you're interested and plan to be releasing a hat or what I forget what they're called, like stripes or tails for the Tiger that'll just fit on top of its UART headers there and add the additional components you need. So once you connect up, you're going to see something like this. This is the debug output from the UART. You'll typically get a lot of really useful information, and most engineers tend to not remove that. So you're not going to see it here because it's already above, but it'll print out information like where addresses are and where data has been loaded at. The one really nice thing about this is it tells us when the firmware was built, which allows us to get some information about the revision of the commit hash that was used for ESPIDF. And that will become important in a little bit as we dive into the very specifics of what the format of various parts of the firmware look like. When you boot into bootloader mode, you're going to see something like this, and this is how you know it's in bootloader mode. It's basically telling you that it's waiting to do something. And so it can vary, but the ESP tool is how you're going to interact with the device. So using ESP tool, we can query the chip. We can get a chip ID. This will tell us the type of chip that it is. It'll give us the MAC address and tell it a little bit more information about it. This is really useful if you want to go and perform any of the hardware attacks that we'll talk about a little bit later, and let you know whether or not it's going to be vulnerable. So here we can see that it's the MAC address, which is useful if you want to find it on your network and you don't have more visibility. But we see that it's revision 1 of the ESP32 D0 WDQ6, and this one is vulnerable to that attack. So now that we have a pretty good background on this chip and the tooling and how we want to interact with it, let's dive into the boot process, because this is where it starts to get interesting and kind of how we're going to start dissecting the firmware images that we're going to pull off. So as the processor boots up, if it's in the normal mode rather than the bootloader mode, the first thing it's going to do is it has this boot ROM, and the boot ROM is what's responsible for loading up the bootloader and the eventual application image. The boot ROM, I believe, is in flash on the chip, and it is not something you can patch, and that's where the vulnerability existed, I believe, in the hardware attacks that we'll link to later. So it's going to load a partition table. The flash itself is broken up into partitions, and these are have different types. You can have multiple applications on there. So if you wanted to do, say, an OTA update and have space to load a new firmware image on, but still fall back if it didn't work, or you wanted to have a testing application, or just multiple applications you wanted to run, you can partition it such that you can have both of those and it can fall back in certain situations. So it loads that partition table into memory, and it will read those partitions and look for an application type image. Once it loads that application, it's going to bring it in from flash, and it's going to load them one after another until there's none left or one succeeds. Once it's loaded in, it's going to parse the application header. You can think of this like an ELF header. Every application is going to have its own header that has some information like the entry point and some information about the segments, and so it knows how to load it into memory once it's grabbed the various parts in. It's then going to iterate through the segments, loading them in at their load addresses, so it tells it where to relocate these chunks to. And then it's going to transfer execution to the entry point of the application, which it read out of the header. So this is important because it's going to tell us how things are booting, where they're booting to, and give us a little bit of information about the flash itself and how to pull out what we care about. If you're interested at all, this is a call stack of what that looks like. You can go into the code and read it for yourself, This is a little bit dated, and so some of the functions may have changed a little bit, but this was relevant and accurate up until at least 4.0 or 4.1, I believe. So there's a few different types of partitions. Your application and data are the two mains, and then within there, you can have different types of data partitions. So there's a data structure called the NVS, or non-volatile storage, and this is used primarily, it's a key value store, and this is primarily used for storing non-volatile data, such as key material, passwords, things that the application needs to store permanently, but needs to have a way to easily recall them without modifying the actual flash image of the application. There's FAT support in here, which gives you like a full file system, which is nice. And a variety of other ones, but those are the few that you're probably going to see most often is applications, NVS, and FAT. So how does this all work? So the bootloader knows where the partition table is. There's a default value that is used that most applications are going to use, which is nice. But as part of the flashing process and the building process, you can change that. Almost always, like I said, it uses the default. But if for whatever reason you're interacting with a device that doesn't use the default, that information should be spit out during boot up, and you should be able to get that from the UART if you need it. So this really is the first step to dumping the firmware, because we need to figure out where everything is. So by default, the partition table is going to be stored at 8,000 hex. The partition table is always 3072 bytes long. And so by using ESP tool, we can dump that segment of flash. This is the tool that I mentioned earlier that is going to be a big piece of how we do our interaction with all these devices. So we use the dump flash subcommand. We give it the start address, the size, and it's going to dump us the partition out of flash. The problem here is that this is a binary file. It's a binary representation of this data because the firmware uses that in order to boot. So Gen ESP32 part is a tool that comes with the ESP IDF. Its primary purpose is for converting back and forth between the binary and the CSV representation. This is used as part of the build process, but it's useful for us here because we can take the binary form and we can turn it back into a human-readable CSV format. So once we do this, we get this partition data. It tells us the various partition names, their types, where they start, and how big they are. There's also a flags field here. For the older partitions and older products, you're not really going to see a lot of use here. Where it is useful is on newer stuff that take advantage of encryption. That's one of the flags that can be used here, where it will ensure that that partition stays encrypted, meaning that we can still read it off, but the data will be, I believe, AES encrypted, and we won't be able to actually read the data. So we can see here that there are two application partitions, and those are what we really are going to care about here. And then the NVS as well, which is our non-volatile storage. There's also some parts of the memory that we're going to want that are not stored on our external flash. There is some internal flash on the device, and the ESP tool dump flash subcommand only works with the external flash. It doesn't work with the internal flash. There's also some various RAM on there that will load data in, such as like for the boot ROM. So we can use the dump mem subcommand, and this allows us to just arbitrarily dump memory. This is really useful if we need to get some of that data, but it's really, really slow. So unless you're looking for specifically data that's is stored in RAM but not stored in flash, I wouldn't recommend using it. The parameters are the same. You just give it the start address, the size, and what you want to write to. As a reference for knowing where to dump, All of this is laid out in the technical reference manual. There's links to this later in the presentation. All of the different families of chip will have a table like this, and elsewhere in the document, it will break down even more to give you an idea of where the registers are and where specific data is stored. But this is a pretty high level overview and gives you information about how the address space is divided up. The other option that you have is just a good old fashioned SPI flash dumper. You can use your FTDI breakout board here to do that instead of talking over UART. I just have a chip clip here wired up to it. And so if your bootloader is locked and you can't interact with it from there, you could still pull off the RF shielding and connect directly to the SPI flash. This isn't going to help you if the flash is encrypted because you'll pull the data off, but you still won't be able to read it. So maybe helpful, may not be helpful, but it's one option. You also may run into problems where the addresses may not line up correctly. The ESP IDF does some form of wear leveling to ensure that you're not destroying the flash, especially for partitions where you're reading and writing a lot, like NVS. And your addresses in your partition table may not align directly with the physical addresses on the SPI flash. If you're doing this, you can either take the SPI flash all the way off the board, or you can try to do it in circuit. Make sure you pull the EN pin low so that the chip won't start up and race you for access to the flash. Otherwise, you're probably going to lose and not be able to dump the partitions out. So now that we've gotten the flash and the firmware off of here, we have to start looking at it and trying to identify secrets, bugs, whatever we're looking for in the device. So Extensa does have support across a variety of debuggers, but the quality is kind of hit and miss. In general, most of the implementations are pretty incomplete or they have bugs because the architecture itself is a little weird. There's also not really a lot of good available official documentation, and the reason for this is that Cadence doesn't make it available. Espressif has licensed the ISA and the cores, and they're allowed to produce this, but they're not allowed to release the documentation. So getting an up-to-date doc about what the ISA is and how it's encoded is not super easy. There's been some leaks. The first link here, the extensa.pdf, is one of those. It came out from, I think, around 2010. So it's available and has information, but unclear as to whether or not it's complete. The second link below is a doc that Espressif has put together specifically for people building compilers and disassembly tools needing to support the architecture. And this isn't official Cadence documentation, but it's probably the best that we're going to get right now in order to help build some better tooling. All of the official tooling right now is based off of GCC, so that's what Espressif ships. I believe it's all upstream as well, so you can get that. There's also official patches that Espressif is building for LLVM and Clang, so eventually it will hopefully land. This has been ongoing for a few years now, and it's not really clear how long it's going to take until it gets upstreamed. But when that happens, it's presumable that it'll probably land in Capstone, which would be nice because all of a sudden you'll be able to add support to more disassemblers. So what tools can actually interact with this? Well, R2 and Cutter probably have the best implementation I've seen so far, and that's because it reuses the GCC infrastructure that is the official toolchain. There's a third-party IDA plugin. I have a fork here that fixes some of the Python 3 issues to support newer versions of IDA. I believe that this fork is up to date with upstream. There hasn't been a lot of work on it, and there were a number of bugs that I found that made it somewhat difficult to use. There's a third-party Ghidra extension that adds support. This will also work with the decompiler, but I don't know how accurate it is. The R2 and Cutter implementation, I believe, will also work with the decompiler, but I think it only works if you use the Ghidra decompiler under the hood. There's talk about upstreaming the Ghidra implementation, but I haven't seen any real movement on it. But there are people still working on it, which is nice. The other big piece that's missing from virtually all tooling is first-party support for loading the firmware images themselves. So one of the sort of irritating things is once you load in the image, you're typically not going to get a lot of very good identification of functions and control flow, just because it doesn't really know where things are loaded and where all that is. Luckily, we can know how to read the format for the header, and so I've written one for IDA, and that's available here at the bottom. I plan to build platform support for Binary Ninja. I don't know if there's support for ESP32, but I'd like to write it at some point in the near future. This loader will work with, I believe, the most up-to-date version of ESP-IDF, but some older versions it won't work with because the format has changed somewhat. It also won't completely load ESP8266 images, as those are somewhat different, but I do plan to add support to handle all of them in the near future. If you're interested what the header looks like, this is it. The main things you care about really are the entry point here and the segments. That's what's really going to help you figure out how to load this thing in. Immediately after, oh, by the way, this is all little endian values. I believe it's a little endian chip, but it might be dual endian. But most of the time, like I've always seen it little endian. Immediately following this header, you're going to see the individual segments. And this is what those look like. You're going to have a load address, followed by a segment length, followed by the data directly, and then the next segment after it. You just take the segment length to go that far in, and you get to the next segment. I briefly talked about NVS as being this data storage mechanism. So other than hard-coded values in the application images and firmware, this is where most of the interesting data is going to live. Currently, there's not a lot of tooling available for interacting with this, but that's something that I'm working on. It's theoretically possible that you could reuse the C++ implementation that they've written in the ESP-IDF to add support to build host-based tooling. The problem is that there's different versions of NVS, and none of the partitions themselves are aware of what version they are. They just depend on the fact that when you compile the whole firmware image, the current snapshot of that knows how to interact with that version of the NVS implementation. And so in order to figure out what the format is, you actually need to figure out which version of ESP-IDF is being used, and then go and parse it the correct way. I believe that there's two different distinct implementations, and the data backend is pretty substantially different. The documentation for all of that's available in their docs, and the code is all open source, so you can go and read it. I would like to build some host-based tooling that allows you to basically interact with it the same way you would, say, like SQLite. It doesn't seem too complicated, but the paging mechanism that they've added in later versions definitely makes it a little bit more difficult than the original version. So I mentioned that a whole bunch of this is based on previous research. And this is really the stuff, if you're going to start diving into this, that you want to go and look at. The first link here is reversing the ESP32 boot ROM. This is the first piece of code that loads up when you start. And there's some really great research in reverse engineering that and figuring out how it works. This is something that's going to be really interesting to you if you want to understand the hardware from a really low level. The limited results links here, this is probably the most interesting research that's come out on the ESP32 family of chips. This is the initial hardware attack that broke the secure boot functionality that has since been fixed and replaced. But this hardware that like came out like that generation is forever broken. So anything that's based on that, if it has the protection enabled, you can still bypass it. The blog posts do a pretty good job of walking through how it works, what the bugs are, and how to replicate it. I haven't gone through and replicated the attack yet, but I plan to pretty soon. It involves voltage glitching to get it back into a known state. The person who did this research is also the one who publicized a bunch of the NRI52 glitching to unlock the locked bootloader again on there. And then again, there's so much documentation that Espressif makes available themselves, and that is really useful and helpful if you start looking into this. It has been immensely helpful as I've tried to understand like how everything works and trying to figure out how to approach some of these problems. There's also tons of tooling they provide as part of the ESP-IDF that makes a lot of this more straightforward. And so definitely looking into that before you go and like write your own, if you don't mind some like manual steps here and there to shift the data from tool to tool. So I want to talk a little bit about next steps and kind of like where I'm looking at. There's definitely been some work, as I said, in terms of like third-party support for building better reverse engineering tooling for this platform. I would like to make that a lot better just because right now, like the state of it is not very good. Disassembler support needs to get better. It's rough and it's doable right now, but it's really, really, really painful. Depending on how well the ESP32C series goes, I think we'll see this naturally sort of just get better, because if Espressif shifts their direction toward these RISC-V chips, the extensive-based ones may just kind of phase out. And, the hardware lifespan for these is super long because they're, IoT things that live forever. But, as the chips move toward that, hopefully we'll just naturally get better support by virtue of RISC-V being well supported already in a lot of the different tools. I mentioned NVS tooling and just getting good host-based tooling to interact with these data stores. That's an area that I plan to focus on and just build out really good tooling for. Right now, you kind of have to do it piece by piece going in there, and it's rough, but like it's really useful because that's where the passwords are. It's where the persistent storage is, and so you have data. Getting all the stuff that I've already done working with the 8266 so that you can look at a lot of the older stuff that's still based on it. A lot of the format itself hasn't changed so much, and so getting it working is really not that big of a deal, but just getting the right code paths in there and making it aware is necessary. And then automating some of the extraction and the recovery of the various partitions. Right now, it's a pretty manual process of having to go step by step, grabbing the partition table, grabbing the individual partitions, converting the partition table from binary to CSV, etc. And so being able to do all that in a simpler, more automated manner would be really nice. And that's all I got. If you have any questions, I'll be around. Happy to answer anything. And if you'd like information about some of the hardware that I was talking about in terms of being able to get the auto reset circuit, I'll be publishing some of the information about that coming pretty soon. I'm hoping to open source all the designs for that and then also offer some pre-built versions of them for sale for anyone who just wants to get one and not have to build it. Thanks.